We have another sorting algorithm that doesn't use comparisons. It's called bucket sort. The idea of bucket sort is to distribute items in a number of buckets, sort these buckets using another sorting algorithm, and then combine them. With this approach, instead of sorting a large array, we sort smaller buckets, and this is going to take less time. Plus, we can sort these buckets in parallel. Of course, that's a very complex topic and goes beyond the scope of this course. But let's see how bucket sort works. So here we have an array of 6 items, and we want to distribute them into 3 buckets. Why 3? No particular reason. Later, I will explain how the number of buckets affects performance. For now, let's just go with 3 buckets. So we need to declare an array of size 3. Each element in this array should be a linked list because it is possible that multiple items go in the same bucket. Now we start iterating over the input array. The first item is 6. Which bucket should we put it in? Here's a simple formula for finding the bucket. We can divide the current item by the number of buckets. 6 divided by 3 is 2, so we should put it in bucket 2. Next, we read 2. 2 divided by 3 is 0, so we should go in bucket 0. Similarly, read the next 4 items and put them in the corresponding buckets. Now we sort these buckets individually using another sorting algorithm. It doesn't matter which algorithm. We can use insertion sort or quick sort. That's an implementation detail. Finally, we start iterating over the buckets array, get each item in each bucket, and put it in the input array. So we go in bucket 0 and read 2. That's going to be the first item in our input array. Now we go to bucket 1. Here we have 3 items, so the next 3 items in our input array should be 3, 4, and 5. In the last bucket, we have 6 and 7, so these are going to be the remaining 2 items in our input array. So this is bucket sort. Now, how many buckets do we need? Well, there is no magic number. The more buckets we have, obviously the more memory we need to allocate, but we can sort each bucket in less time because we would have fewer items in each bucket. Now let's do complexity analysis. What is the space complexity of bucket sort? Well, assuming that we have k buckets, we need to allocate an array of k items. Each item in this array is going to be a linked list. The total number of items across all these linked lists is equal to the number of items in our input array. That is n. So the space complexity of bucket sort is O of n plus k. What about time complexity? Well, first we need to iterate over the input array and distribute items to different buckets. That's an O of n operation. Then we need to iterate over the buckets array, sort each list, and put the items back in the input array. Iterating over the buckets array is an O of k operation because we have k buckets, right? What about sorting? Well, we should consider the best and worst case scenarios. In the best case scenario, in each bucket we have a single item. In this case, sorting will be an O of 1 operation, but that would be at the cost of allocating so much more space. So in the best case scenario, the time complexity of bucket sort is O of n plus k. If k equals n, the time complexity will be O of 2n, which we can simplify to O of n. So that's linear time. Now, in the worst case scenario, all the items are in a single bucket. Here, bucket sort will take the time complexity of the underlying sorting algorithm. For example, if we use insertion sort, the time complexity will be O of n squared. So overall, the time complexity of bucket sort can range from O of n to O of n squared. And this is dependent on the number of buckets. If we allocate more buckets, our algorithm runs faster, but of course, this will come at the cost of extra memory. If we reduce the number of buckets, we save memory, but our algorithm gets slower. Again, this is another example of time-memory trade-off in computer science. There are a lot of situations where we can make a program or an algorithm run faster, but at the cost of allocating extra memory. So we have to do a trade-off between the execution time and memory. All right, enough theory. Now spend 20 minutes and implement bucket sort. Then come back see my implementation.